Alright, so today we want to look at the area under a curve. We'll actually probably look at length of a curve as well. So last time finding the tangent at a particular point on a curve. We're also looking at the first and second derivative of the cavity and where we have horizontal and vertical tangent lines. Okay, so we know that if we wanted to find the curve, we've done this plenty. So if we had a curve that defined by y as a function from and we want to find the area under the curve from x being a to b, we just do from a to b of the whatever the function is. And we know that if we do the function from a to b, then we will get the area under the curve. Okay, so of course we're going to do the same thing for parametric curves. We just have to kind of figure out how to do it when we have sort of when it's defined in terms of two functions instead of one. So if the curve is traced out once by the parameter, and that's very important because we know that some equations cause the function to be, you know, go over along the curve multiple times. So, you know, we've seen ones where they go around the circle twice, or where there's part of a parabola and it swings back and forth, sort of, you know, those things define pendulums actually. So we have to make sure we pick the part of the curve where it only traces it out once, and as long as we trace it out once, then we can calculate the area under the curve using, you know, what we would expect to. We start with the area goes from a to b of y dx. So y is just this, another way to say f of x. Okay, but if we use the substitution rule, when we substitute for y, well, y is a function of g, so we're going to substitute that in there. And then dx, well, if we want to find dx, we've got to take the derivative of the x formula. Okay. And then we need to change the bounds to go from alpha to beta. So the bounds have to be in terms of t because everything is now written in terms of t. So we're just using the substitution rule on this. Okay. And then, you know, sometimes depending on the curve, you might have to go beta to alpha or alpha to beta depending on what the curve looks like if you want to get a positive kind of area. And you'll know usually that you went the wrong direction if you get a negative area, and in that case, you know, sometimes you can just, you know, change the sign and go, oh, I should have gone beta to alpha instead of alpha to beta. Okay. So let's look at an example. So we want to find the area under just one arch of the cycloid. So we're talking about, you know, this, we want to look at the area under, let's just say, this one arch. Okay. And so we've looked at this before. So if we're looking at this point right here, the x value would be 0, and here the x value, we know that is gone the entire circumference, so this would be 2 pi r. Okay, so if we were doing the area under the curve, we would do the integral from 0 to 2 pi r. Those are the bounds of x of y dx. Okay. And so then we will use the substitution rule. Okay, I'll do the bounds in a second. Okay, the y value is r times 1 minus cosine of theta. And then the dx, we've got to take the derivative of this. So the derivative of this is r times 1 minus cosine of theta d theta. And now we need to find the bounds. Okay, so when x is 0, okay, we need to figure out the theta that would correspond to that. So we would do 0 equals r times theta minus sine of theta. Okay, or 0 equals theta minus sine theta. Okay, or the angle equals the sine of the angle. Okay, so if you think about that, the only time that the angle equals the sine of the angle is when the angle is 0. So this gives us theta equals 0. So that will be our lower bound. And then our upper bound at 2 pi r, so when x is 2 pi r, we need 2 pi r equals r times theta minus sine theta. So divide both sides by r. So we have 2 pi equals theta minus sine of theta. Okay. And if we think about that, when will the angle minus the sine of the angle be 2 theta? So for example, if I did 0 for my theta, I would get 0 minus 0. That would not be 2 theta. Okay, but if I put 2 theta, 2 pi in here, well, 2 pi minus the sine of 2 pi, well, the sine of 2 pi is 0. That will give us a 2 pi. So this will be when theta is 2 pi. Okay, so that's our bound up here. All right, and so now we have everything in terms of our parameter, and we should be able to just take the integral. Okay, so let's rewrite this. This is 0 to 2 pi of r times r is r squared. I'm going to actually pull that out front. And then I have 1 minus cosine of theta times 1 minus cosine of theta, or 1 minus cosine squared of theta. Okay. Probably for this particular integral, it's best if we go ahead and expand that out. So I'm going to have r squared, the integral from 0 to 2 pi, and we square that, I'm going to get 1 minus 2 cosine theta plus cosine squared of theta. And so this is easy to integrate. This is easy to integrate. This one we need to do a substitution though. Okay, so the 1 is good, the minus 2 cosine theta is good, but the cosine squared, we want to substitute that with 1/2 of 1 plus cosine of 2 theta. Alright, and then if we simplify that before we actually do the integral, it'll make it easier. Okay, and so we're gonna have a 1 and then plus a half, so that's going to be 3/2. Then we have the minus 2 cosine theta, and when we distribute this through, we'll have a 1/2 cosine 2 theta. Alright, so that should be simplified enough now that we're able to do the integral. And so when we do that, we still have our r squared out here. Okay, so when we integrate 3/2 with respect to theta, we'll have 3/2 theta. When we integrate the negative 2 cosine theta, we'll get negative 2 sine theta. And then we'll have plus 1/2, and then when we integrate this, we'll get 1/2 of sine 2 theta. And that all needs to be evaluated from 0 to 2 pi. Alright, so when we put the 2 pi in, so we'll have 3/2 times 2 pi. And then minus, when we put 2 pi in, the sine of 2 pi is just 0, so this one goes to 0. And then we'll have plus 1/4 of the sine of 2 times 2 pi, that's 4 pi, but the sine of 4 pi is just 0, so this one's also 0. Let me put this one in parentheses, and then minus, and when I put 0 in here, well, 3/2 of 0 is just 0, sine of 0 is 0, that one's just 0, sine of 0 is still 0, so that one's just 0. Okay, so this is really just r squared times, oops, so this is supposed to be 2 pi. I thought I lost a, yeah, so I should have put 2 pi in there, sorry. So those cancel out, and this will just be 3 pi, and then I've got minus 0, and all the rest of that is minus 0. So this is just 3 pi r squared. Oops. Okay, and so what's interesting about this, okay, is that the area under one arch of a cycloid is 3 times, and so I'll just write out times. And notice pi r squared is the area of a circle with r square with a circle of radius r. So it's 3 times the area of the circle that generated the cycloid. So you have the circle that was rolling along that generated that cycloid, and the area under one arch is 3 times the area of that circle. It's kind of interesting. Okay. So that is an example of area under a curve. Another thing that we have done is to find the length of a curve. So let's do that with parametric curves. So we know that if we want to find the length of a curve given by y equals some function of x, okay, is we just take the integral from a to b of the square root of 1 plus the derivative squared. Okay. So if we want to do that with parametric equations, once again, it's important that we traverse the portion of that curve only once. We'll do an example later on where you'll see why. But so using the substitution rule on this one, once again, since we're changing to the parameter value, we're going to change the bounds to the appropriate bounds for that variable. And then we would substitute, the way that we find the derivative of y with respect to x is we do the derivative of y with respect to t over the derivative of x with respect to t. Okay. And then the derivative of x is really just the derivative of x with respect to t dt. That gives us, if we cancel those, we just get dx. Okay, and if we simplify this basically by taking this and moving it from outside, right now it's not under the radical, so if we move it inside the radical, to move it inside we've got to square it, right? If we move something outside of a radical, we have to take the square root. To move it inside of a radical, we have to square it. So we would square that when we move it in there, and then distribute that to both of these, and so that's where we get the dx squared, and this denominator cancels, and you just get dy dt squared. Okay, so this is the simplified form, and this is the formula that we'll want to use for finding arc length. Okay, so we're going to do 2 separate arc length examples, and then discuss kind of the relationship between these two things. All right, so first of all, we've got x is cosine t, y equals sine t. Those should look familiar. We looked at those at this parametric equation in the previous in section 10.1, so you should have an idea maybe of what that is, but we'll talk more about that after we finish it. Okay, so we want to find the arc length. We know that the arc length is going to be the integral, I'll just write this out, from alpha to beta. So those are in terms of the parameter. And then the square root of, and then we do dx dt squared plus dy dt squared dt. So that everything is in terms of our parameter. So for this particular equation, our parameter goes from 0 to 2 pi, so those are the bounds that we'll put on our integral. And then dx dt, well, that will be the derivative of cosine, which is negative sine of t. Now we have to square that. And then dy dt, So the derivative, or dy dt, is going to be cosine of t. And we got to square that, dt. Okay, so we've got from 0 to 2 pi of, and then this is sine squared t, and this is cosine squared of t. And we know that sine squared plus cosine squared is just 1. So we've got the square root of 1, or the, which is just 1. So we've got the integral from 0 to 2 pi of 1 dt. Well, that's an easy integral. Okay, so we just have t evaluated from 0 to 2 pi, or 2 pi minus 0, which is just 2 pi. Okay. All right. So if you think about this, we've seen this before. This is actually the unit circle, right? So if I think of this as, x equals r cosine theta and y equals r sine theta, that's our, default start at on the positive x-axis, and our theta angle will go counterclockwise. And so if I have an r value of 1, that's going to give me x equals cosine theta and y equals sine theta. And that's exactly what I have. Okay, so we're talking about the circle, okay, that starts here at 1, and then it goes around this direction counterclockwise. Okay, so if we were doing the arc length, well, that's really just the same thing as the circumference. So the circumference of this circle would be 2 pi r. R is 1, so sure enough, 2 pi times 1 is 2 pi. And the arc length is exactly what we would expect for it to be. Okay. So this goes with A. Okay, so for B, let's do this one. So the arc length, again, is the integral from alpha to beta, so 0 to 2 pi. Okay, and then the square root of the derivative of x with respect to t, so that's this one. So this is going to be, cosine of 2t times 2, or 2 cosine t squared. And then we've got to do the derivative of y with respect to t squared. So that will be negative sine of 2t times 2 squared dt. Alright, and so if we square this, we're going to get 4 cosine squared of t. If we square this one, we're going to get 4 sine squared of t. If we factor out the 4 underneath there, 4 times cosine squared t plus sine squared of t. Well, this is really just 1. The square root of 4 times 1 is 2. So this is going to be 2 dt. That's, again, pretty easy to take the integral of, so that's going to be 2t evaluated from 0 to 2 pi. So that's going to be 2 times 2 pi minus 0, or 4 pi. Okay, so the arc length is 4 pi. Now, again, this is also a circle. Okay, so, but this one, because the sine is with x and the cosine is with y, okay, that one actually starts up here and goes around clockwise, so it goes this direction. Okay. And because there's a 2 in here multiplied by the parameter, it actually traverses twice. So it traverses the circle twice between 0 and 2 pi. Okay. And so what we're getting here for the arc length is it starts here, it goes around once. That will be 2 pi, and then it goes around again. Another 2 pi is giving us 4 pi. Okay, so in terms of the length of the parametric curve, it is correct. Okay, we've got that it goes around twice, so that is going to give us 4 pi. Now, if we were just wanting the arc length of the curve associated with these equations, that's why I have emphasized back here, if we just want the length of the curve and not the length of the parametric curve, then we would need to make sure that the curve is only traversed once. Okay, and in here, we don't have that the curve is only traversed once. We have it's traversed twice. Okay, so to ensure that the curve is only traversed once, we would need to restrict the parameter to be between 0 and pi. That would give us one iteration. So it goes around once in pi radians, and then another again in another pi radians. It goes around twice in 2 pi radians. So if we were wanting just the length of the curve associated with the parametric equations and not the length of the parametric curve, then we would want to make sure that we restrict it to be going only around once. So just a little subtlety. So when you look at a problem, are they asking you for the length of the parametric curve or the length of the curve associated with that? If that's the curve associated with it, make sure that you're restricting the parameter to make sure that it only goes around once. Okay. All right. Next, let's look at the length of one arch of the cycloid. So we're looking at, the length of this. We've already looked at the area under there, but now we're actually looking at the length of that. Okay, so we've seen previously that if we're looking at the arch of one, our theta will be between 0 and 1 complete revolution of a circle. Well, it makes a complete revolution in 2 pi radians. So the angle, our parameter will be between 0 and 2 pi. Okay, so the length is the integral from 0 to 2 pi of the square root of the derivative of x. So we've got to do this one. So it's r times 1 minus cosine theta, and this whole thing needs to be squared, plus the derivative of y with respect to the parameter. Okay, so that's going to be r times sine of theta. That needs to be squared, d theta. Alright, so let's simplify this a little bit. Okay, so we're going to have r squared 1 minus cosine theta squared plus r squared sine squared. Let's go ahead and multiply that out. And let's also factor out. So if I were to factor out an r squared from this, I'll do that as well. Okay, so I'm going to factor out the r squared, and then this, I'm going to go ahead and expand it in the same step. So this will be 1 minus 2 cosine theta plus cosine squared of theta. And factoring out the r squared, this one's just going to give me sine squared of theta. Okay, I know what the square root of r squared is. I can bring the r out, and I'll just take it, since it's a constant, I'll take it outside of the integral. And then sine squared plus cosine squared is 1, so I have 1 plus 1 is 2. Okay, oh, I made this too long. Okay. And it's probably easy if I just go ahead and factor that 2 out as well. So when I factor out the 2, I can bring the square root of 2 out. So I'm just going to make this square root of 2r. And then I'll just be left with 1 minus cosine under my radical. Okay. And now this is a little bit tricky to integrate, but what we can do is, oh, you know what? I think I should have left the 2 in there. Sorry. I'm going to leave the 2 in here. All right. And you'll see why in a second. All right. So we know, like this 1 minus cosine, we've kind of seen a substitution for that, but instead of having a 2 there, we've had a 1/2 there. So if I had a 1/2 of 1 minus, but then it's cosine of 2, and let me just call it u. Okay. That's what we get for the sine squared of u. And this looks very similar to that, except that there's a 2 there. Well, how would we get a 2 there? We just make this 4 sine squared of u equals, and then that would give us the 2, 1 minus cosine squared of u. Okay. So if we can just do a u substitution so that this is 2u instead of theta, then we've already got the 2 there. That's why I was saying that we want to do it this way. Okay, and so instead of theta, we want that theta to be 2u. So if we do that substitution, that theta equals 2u, then we can make that, then we'll have this nice, and we can substitute it with 4 sine squared of u, and it should be fairly easy for us to integrate. Okay, well, if theta is 2u, then that we have that theta over 2 is u, and so that 1/2 d theta or sorry, I went the wrong way. U equals 2 theta because we want this to be a 2u. Yeah, so theta equals 2u. And so then, no, I think I have this right. 1/2 d, sorry, equals du. Okay. So let's figure out our substitutions here, and let's see if I did this right. Okay, r equals, okay, and in here 2, 1 minus, and we want this to look like cosine of 2u. So 2u has to be the same thing as theta. That sounds right. Okay. And then d theta. Okay, d theta is actually going to be 2 du. Okay, and then we need to get our bounds here. All right, and to find our bounds, all right, well, when theta was 0, okay, we know that So when theta is 0, u must be, so for 0 equals 2u, so u has to be 0. And then when theta is 2 pi, so I'm going to have that 2 pi equals 2u, so that u must be pi, so we're going to have a pi there. Okay. All right, so we've got r from 0 to pi. Okay, and we know that here, if I've got 2 times 1 minus the cosine of u, for that I can substitute in 4 sine squared of u. So this is really 4 sine squared of u. Of course, I've got the square root there. I'm going to pull this 2 out front. Okay, and so this is going to be 2r integral from 0 to pi of, I'll take 2, and then times the absolute value of the sine of u. Okay, I guess I need to kind of go over here now. Okay, so I'm going to pull that out front. I'm going to have 4r times the integral from 0 to pi of the absolute value of the sine of u du. And that's going to be 4r times, well, I guess I can, the absolute value of the sine from 0 to pi. From 0 to pi, it's always positive, so I can take the absolute value bars away. Okay. And so I get 4r times negative cosine of u evaluated from 0 to pi. So that's 4r. Okay, and then the cosine of pi is 1, so this will be negative 1, and then, oh sorry, it's negative 1, so that's negative 1, which is positive 1. Cosine of pi is negative 1, so negative 1 is positive 1, and then minus the negative cosine of 0. The cosine of 0 is 1, so that's minus negative 1. So I've got 1 plus 1 is 2. 2 times 4 is 8. That's 8r. Okay, and that is the arc length. So once again, this is an interesting result. Okay, so this means the arc length of one arch of the cycloid is 8 times the radius of the generating circle. So there was a circle rolling along here that generated that, and the length of the arc is 8 times the radius of whatever that circle was. Okay. All right. Our last example for this section is to now look at something three-dimensional. So we're looking at surface area. For this problem, we want to adapt the formula for surface area the way that we did previously for arc length. So if you remember the way that you find surface area, as it's 2 pi times the radius, which is y. You know, if I were to draw a curve, let's say I'm taking some curve, whatever, from point A to point B. Okay, well then I'm going to rotate it, you know, around some axis to get a surface. Okay, and so then I'm going to get all these circles along here, right? So if I want to find at the surface area, I just add up this circle and this circle and this. I add up all these circles, and that'll give me the surface area of this surface. Okay, and so the way that I find the circumference of this circle is I do 2 pi times the radius. Well, the radius of that circle is whatever the y value is of the whichever circle I'm going along. And how many circles do I have to add up? Well, I have to go all along this length of the arc, right? So remember, intuitively, that's how we find surface area. So it's the circumference of the circle. How many circles do we have? Well, so whatever the length of is the arc that we use to generate the surface. Okay. So, so here's our arc length for the parametric curve, and then, you know, it's just 2 pi times the radius of y. All right. So, using that formula for surface area, we want to show that the surface area of a sphere with radius r is indeed the formula that we know, 4 pi r squared. Okay, so how would I generate a sphere? Well, the way that I can make a sphere is that I can take a semicircle. Let's say a semicircle like this with radius r. Okay, and if I just take that circle and then I rotate it around the x-axis, I'm going to get a sphere of radius r. All right, so how can I get a semicircle? Well, we know the general equation for a circle of radius r is, well, x equals r cosine theta and y equals r sine theta. Now if I want a semicircle, you know, this is what gives me the starting point here. Okay, I guess I should have put my axes in the middle there. Yeah, so that would be with the axis there, not here. Okay, and so this would, so if I only want half the circle, then I have to restrict my theta between 0 and pi. Okay, so that'll just give me this portion. It won't give me the rest of it, and then I can take that semicircle and rotate it around the x-axis to give me the full sphere that I'm looking for. Okay, so if I'm looking for the surface area, okay, I want my theta only to go from 0 to pi. Okay, and then going back here, I want 2 pi times y. So 2 pi, you know, if I'm looking at any random circle along here, right, this y value is going to be the radius of that circle. Well, y is r sine theta. Okay, and then the arc length is given by the square root of dx dt, so that was going to be negative r sine theta, and that needs to be squared. And then we add on dy dt squared, so that will be r cosine theta, and then d theta. Okay, so let's simplify this a little bit. This will be from 0 to pi. This is 2 pi r sine theta, and underneath here we've got r squared sine squared of theta plus r squared cosine squared of theta. Okay, and then If we were to factor out the r squared, we would just have r squared times sine squared plus cosine squared is 1. So we just end up with the square root of r squared, which is just r. So this is, we're going to pull the 2 pi r squared out, and we're just left with sine of theta. Okay, and so we have 2 pi r squared, and then the integral of sine theta is negative cosine theta, and that's evaluated from 0 to pi. And so we have 2 pi r squared times, okay, the cosine of pi is negative 1, negative 1 is 1, and then minus the negative cosine of 0, so cosine of 0 is 1, so that would be negative 1. 1 minus negative 1 is 2, so this gives us 4 pi r squared. Okay, so indeed the surface area is 4 pi r squared. Okay, so we already knew that, but this is how we can, you know, it's always nice to do examples where you know what the answer is supposed to be, and then when you get that answer, you're like, yeah, I did it right. Okay, so the surface area of a sphere is indeed pi r squared. Okay. All right, so that is calculus with parametric equations. You just got to plod through it slowly. It's a little tricky until you get the hang of it, but then I think you'll be fine.